All right, so we're in 10.5 now. And 10.5 is going to revisit something that you've talked about back in intermediate algebra, the topic of complex numbers. You should have already learned about complex numbers by this point, but we are going to do a quick review of them. So complex numbers start with a discussion of this number that we call I. I is typically what we think of as the square root of -1, or alternatively, we can think of it as the number that you can square to get -1. We know that there are no real numbers that you can take that are the square root of a negative number. Normally, we just say you can't take the square root of negative numbers. However, we invented a number, I, that fulfills that role, something that you can square to get a negative. A lot of people struggle with that concept because they don't like the idea of inventing a number just seemingly out of thin air, and that's an understandable difficulty. However, if you continue on in math, you learn that literally every number is invented, even though some have more natural interpretations physically than others. There is no, the number that we call I is no more real or imaginary than the number 1. And as long as the numbers, as long as this fulfills a useful role in mathematics, it is as valid of a number as any other. So what then do we mean when we talk about complex numbers? Well, complex numbers are numbers of the form a plus bi, where a and b are real numbers. So examples of complex numbers would be 3 minus I. Notice that it's of the form a plus bi, where a would be 3 and b would be -1. 2 is a real number, but it's also a complex number because you can think of it of a number of the form 2 plus 0i. 0 times I is still 0, so it would simplify to this. Same thing with this, 2 minus 2i. That's also a complex number. Now, when we work with complex numbers, you usually start with the basic arithmetic that we use on complex numbers: adding, subtracting, multiplying, and dividing. So, for example, if I wanted to add addition, if I wanted to add two complex numbers, it's essentially just combining like terms. So if I have this, -6 plus 2i, 2 plus 3i, that's one complex number, plus -6 plus 2i, another complex number. Addition is just combining like terms. 2 plus -6 would be -4. 3 plus 2 would be 5. Now these numbers here, the a and the b, we call these the real and imaginary parts. bi is not the imaginary part, just the b. It's the coefficient. So when you hear me say things like add the real parts and add the imaginary parts, we're doing what we did here. Subtraction is similar. If I had something like this, 3 plus I minus 4 minus 6i, something like that, I would imagine distributing this minus sign and then still combining like terms. So that would be 3 minus 4, which would be -1. I minus -6i. That's the same thing as I plus 6i, which is 7i. So for addition and subtraction, complex numbers feels the exact same as adding and subtracting linear expressions. You know, you think of that I as if it were a variable, like an x or something. Multiplication and division are where this looks a little bit different. So for multiplication, for example, if I wanted to do something like this, 3 plus 4i times 2 minus I. It starts off looking like a product of two binomials. We can FOIL this. Notice if I were to FOIL, I would have 3 times 2, which is 6, 3 times -I, which is -3i. 4i times 2, which is plus 8i, and then 4i times negative I, which would be minus 4i squared. And here's the first time where we really need to use the definition of this number I. So first of all, I is the number that you can square to get negative 1. So this is actually negative 4 times negative 1, which is positive 4. This becomes 6 minus 3i plus 8i plus 4. Okay? And then at this point, it's just simplifying. I have 6 plus 4. Those are real parts. That makes 10. Negative 3i plus 5i. Those are the imaginary numbers here. It's going to be 5i. Okay, so we're using the fact that I squared equals negative 1. Actually, before we move on to division, I want to do one more example of multiplication. Suppose I had 3 minus 5i times 3 plus 5i. Well, again, if I expanded this out, it's going to become 3 times 3, which is 9. Plus 3 times 5i, that would be 15i. Negative 5i times 3, that's minus 15i. And then negative 5i times 5i, which would be negative 25i squared. Notice that the 15i and the negative 15i will cancel each other out, and I'm left with 9. This I squared becomes negative 1, changing this from a negative 25 into a positive 25. Okay, and that gives me 34. Now this is an important example because these two numbers are what we call conjugates. Conjugates. Or more specifically, complex conjugate. The word conjugate is used for a lot of different things in math. What we mean when we talk about conjugates of complex numbers, it's a pair of complex numbers that look almost the same, except of the only difference is the sign on the imaginary part. So where I have a minus here, I'm going to have a plus here. That makes this the complex conjugate of this, and this is the complex conjugate of this. A property of complex conjugates is that when you multiply them together, you always end up with a strictly real number. No i's here. And the reason that happens is because of this. When you multiply conjugates together, the I terms will cancel each other out. Also worth noting is that the end result, if you go back to this step right here, is actually the sum of the squares of the real and imaginary parts. So 3 squared plus 5 squared, that's 9 plus 25, giving me 34. That's not unique to this example. That'll happen anytime I multiply complex conjugates. So we can actually do problems like this much, much faster if we just remember that. Another example here. If I do 7 minus 2i times 7 plus 2i, rather than go through all the work of foiling that, I'm just going to remember that this is the sum of the squares of the real and imaginary parts. 7 squared is 49. 2 squared is 4. It's going to be 53. That's a very useful shortcut when working with complex numbers. Okay, let's talk about division for a moment. Let's suppose I wanted to divide 3 plus I by 1 minus 2i. So division, we don't think of division in the same way that we think of division with integers. I'm not thinking how many times does this go into this, because I don't really have a sense of quantity with these numbers. It's hard to visualize that. Instead, the goal is just to find a way to simplify this expression so that it looks like something of the form a plus bi. And the trick is to use the conjugate technique that we just talked about. Just like with any other fraction, I can multiply the numerator and denominator by the same thing, because that's equivalent to multiplying by 1. If I multiply this by 1 plus 2i over 1 plus 2i, and this 1 plus 2i I'm getting because it is the conjugate of my denominator. Okay, so in my denominator, I know that multiplying these two conjugates together gives me the sum of the squares of the real and imaginary parts. 1 squared is 1, plus 2 squared, which is 4. Up here, I have to FOIL these out. Imagine these being in parentheses. I would multiply that out, so that's going to give me 3 3 times 2i is 6i. I times 1 is I. And then I times 2i is plus 2i squared. Okay. Now, my numerator, I know that this 2i squared is going to become a negative 2 when the I squared becomes a negative 1. 3 plus negative 2 would be 1. And then 6i plus I combines to 7i. My denominator, 1 plus 4, gives me 5. Now, we're almost there. The key thing was the fact that I was able to get a real number in my denominator. Now what I'm going to do is split this into two fractions and bring the I out of the second fraction, writing it as 1/5 plus 7/5 I. That's the same thing as this. But now my complex number is of the form A plus BI. And that's really all there is to division. We multiply by the conjugate of the denominator, simplify until you get something of the form A plus BI. Okay? Next up, I want to talk about powers of I. So if you take I to the power of 0, we treat that the same way as anything to the power of 0, except for 0 to the power of 0. That's equal to 1. We know that's true for real numbers. It's also true for imaginary numbers. I to the first power, just like anything to the first power, is itself I. I squared, by definition, is negative 1. Okay, so we know this. We haven't ventured into this territory yet. What is I cubed? Well, if I cube I, that's like taking I squared and multiplying it by I one more time. But if I squared is equal to negative 1, that's the same thing as multiplying negative 1 by I, which would be negative I. Negative 1 times anything is the opposite of that thing. One more time, if I multiplied this to the fourth, or sorry, if I did I to the fourth power, what's going to happen? Well, again, that's like taking the previous result and multiplying it by I one more time. But if I cubed is equal to negative I, multiplying this by I gives me negative I squared, which is the same thing as negative 1 or positive 1. And if you notice, we are now back to where we started. So every step of the way is going to repeat this cycle of 4 solutions. 1i, negative 1, negative I. Now, keeping this in mind, this actually gives us a way of raising I to much larger powers without much work. Because, for example, if I wanted to do I, let's say, to the 54th power, well, if I were to divide 54 by 4, and thinking of this in terms of long division, okay, 4 goes into 5 once, that's going to give me a 4 here, subtract, I got a 1, bring down that 4, 4 goes into 14 3 times, 4 times 3 is 12, subtract, I get a 2 here. Before you talk about decimals and fractions and all that, early on in elementary school, you're taught to call that to the remainder. And what that really means, if you put this all back together, is that 4 times 13 plus the remainder of 2 is equal to the dividend, which was 54. The purpose of doing this is that I can rewrite my exponent this way. This is equal to I to the 4 times 13th plus 2. Okay, that may seem like a bizarre thing to want to do, but now I can use exponent properties to represent this differently. I know that this would be the same thing as I to the 4th to the 13th power, because that's what a power to a power looks like. You can multiply those. 4 times 13 becomes I to the 4th to the 13th. Adding a power is the same thing as multiplying by I to that power. So I'm using exponent properties to split this up. Now, I to the 4th is equal to 1, and 1 to any power is just 1, and 1 times anything is itself. So this whole thing reduces just down to I squared. Notice that I squared was the remainder. I squared we know is equal to -1. So I can bypass all of this stuff if I just change I to the 54th into I squared, I to whatever my remainder was. One more example like that. If I wanted to do I to the 103rd power, I just would take 103, divide it by 4, and I'm using 4 because that's how many different answers there are in this cycle, this pattern. If I were to do that division, I would end up with 25 with a remainder of 3. The 25 doesn't matter. It doesn't really play a role anywhere. What matters is the remainder. This will end up being the same thing as I cubed, which is -I. Okay, that's going to be it for this video. In the next video, we'll talk about a graphical representation for complex numbers, and that's really where we start to use the trigonometry.